thanks for participating. And we're going to start with Hydraulic Inspection Vehicle Explorer Culvert Upgrade. And Dan, if you could introduce yourself and get started.
Yes, thank you. So let me see if I can share my screen here. All right, can everyone see and hear me?
Yes.
Okay, so thank you. I'm going to talk about a project going on at UVM, which is an update to the culvert inspection vehicle. So there we go. All right. So an overview of what exactly we're working on here. As we know, proper inspection of small culverts can prevent roadway failures, avoid traffic disturbances, and hopefully head off more costly repairs. So currently VTrans uses two different culvert inspection vehicles. The Hydraulic Inspection Vehicle Explorer, the HIVE, is low cost, works well, but has a limitation in its ability to transmit video from deep within long culverts. And so that's shown on the top left. And below that is the crawler, which is extremely effective and durable, but requires a team of 2 people and a support van, which makes it expensive and logistically difficult to deploy out to many inspection locations. So we're working on a HIVE 2 design, which will meet VTrans requirements for efficient and low-cost culvert inspection. All right, so a bit about how this problem was approached. We used a 1/16 scale remote control toy tank as the chassis, which seems a little odd on first glance, but it's extremely durable. And the continuous tracks let it meet certain VTrans specifications, such as being able to clear a 6-inch separation gap and remain stationary on a 20-degree slope if you're not giving it any input controls. So one of the major focuses was to determine optimal equipment for radio control and video transmission through culverts. So this was done through a theoretical analysis and then a series of field tests. At the end of the day, the total materials cost came in just under $1,500. So here I'll start out with just kind of 2 of the major results here. So when the HIVE 2 was equipped with the 5.8 gigahertz transmission system that we settled on, it provided up to 100 feet of additional range when operating in a 30-inch drop inlet when compared with the original HIVE. And gave over 50 feet of additional range when operating an 18-inch culvert when compared with the original HIVE. So 2 significant performance increases there. And finally here, I'll just highlight on the top right a series of performance metrics which were where the original HIVE inspection vehicle didn't quite meet the specification VTrans was looking for, and areas in which the HIVE 2 has exceeded that capability. So in all, the HIVE 2 gives greater operating range, better ability to traverse obstacles and gaps within culverts, and it also has precise distance encoding using an attached tether and a spool with an encoder on it. So if you find a defect in a culvert or an area of interest, you know exactly how far into the culvert you're looking. And then finally here I have 2 stills from video that was taken with the HIVE 2. On the left we see a culvert with a partial blockage and there's sediment on the inlet side. And then after the vehicle traverses over the blockage, we see that now the culvert is clear and that the vehicle was able to traverse that obstacle. So thank you very much. That's just my quick spiel here.
Thank you. Up next, Todd and Holly.
Hello, my name's Todd Eaton. I am the Technical Assistance and Training Specialist for Vermont Local Roads. If you're not familiar with Vermont Local Roads, we are what's called an LTAP, Local Technical Assistance Program. Every state in the country has one. And so I'm going to share my screen here and just show you our poster. So what we have become aware of through the time that we've that Vermont Local Roads has been part of VTrans, we've noticed that many municipalities have several challenges as far as resources and budgets, and that they continue to to find themselves in positions where they're reacting to their roadway network challenges rather than being able to manage it and kind of look ahead and plan as far as their maintenance and management of those roadway networks. And so the efforts that Vermont Local Roads has applied to develop quality and engaging GIS training to municipality really tightly parallels VTrans' mission and vision to provide safe and efficient movement and affordability. In addition, this also fulfills Vermont Local Roads' mission to foster a safe and efficient and environmentally sound surface transportation system by improving the skills and the knowledge of the municipal transportation workforce and decision makers.
Massachusetts. So here.
Sorry, if you'd mute yourself. Yeah. So what we're looking to do here is we've utilized these stick funds to purchase 10 iPads to use in training to give a hands-on, which will increase the engagement and the learning retention of the municipal workforce and decision makers that we have in our workshops to actually understand how to do the data collection and operate and maintain a GIS-based asset management program. There's been some, the COVID-19 is and the lockdown and the pandemic has really presented some challenges, but we have we remain determined to work through it, and we're finding different ways to provide this training and utilize these stick funds in a virtual world now as we readjust and kind of continue to push ahead. So our timeline has been pushed back to in the spring when we'll begin to actually provide these trainings, but we have purchased the iPads for the training purposes specifically. And as we move ahead and I guess shore up the process for actually gifting iPads to certain municipalities who commit to building a GIS-based asset management program within their town, we'll with these stick funds, we'll provide an iPad and we'll work alongside them to make sure that they are successful in their efforts to establish, again, a GIS-based asset management program. Thank you.
Wow, you were right on. Thanks, Todd.
Oh, look at that.
Next up, we have Sarah.
I'm Sarah Linn. I work for VTrans in the Maintenance Bureau as the sole GIS professional, and I'm going to attempt to share my screen here.
Excellent.
Perfect. Okay, so for any of you that are not familiar with the Maintenance Bureau, we're responsible for maintaining thousands of miles of roadway, and we have hundreds of employees. The Maintenance Bureau includes a wide range of positions from boots on the ground, roadway maintenance and plowing, all the way up to managers who act as decision makers. In my role as a GIS professional, I use this guiding question when approaching any project. So how can we use GIS resources to improve maintenance, data accessibility, and streamline maintenance processes? In the past, the Bureau used communication tools that were available to them at the time, so maybe direct verbal communication, email, handwritten notes, map notations. Often these methods were unique to districts within the Bureau and could make for clunky communication and data sharing. These days, the ArcGIS platform provides good solution for creating easily accessible data, and I'm going to share a few of those examples with you now. Sorry. The first example is an application called the Morning Report, and in this application, we've created a process where maintenance staff can input their expected daily maintenance plans into a mobile application. The data is then displayed on a dashboard for viewing, and this allows people within the Bureau to easily access and view that data, but it also enables us to inform the public about how they can, how traffic may impact their day. Next example is a process created for assessing storm damage to roadway infrastructure. And again, kind of the same process where data is collected in or created in the field and then displayed on a dashboard. But a powerful feature of this particular process is that the dashboard allows real-time access to data and automatically generates an estimated cost of repair. And this enables decision makers to quickly determine whether we'll need to apply for additional federal resources to get our roadways reopened quickly and efficiently. In the final example, this is still in development, but the goal of this application is to develop a GIS system that allows maintenance staff to identify guardrail damage, the estimated cost, the current status of repairs, or repair deadline information. But the tricky part of this project is that guardrail damage is constantly occurring and being repaired, so keeping the data current kind of poses a challenge. And last, in conclusion, we've learned that GIS is a perfect tool for what we need in the Maintenance Bureau, which is, data management, data accessibility, and data transparency. And each of these projects and every project poses its own unique challenge. And it can be tricky to find the right GIS tools for both the type of data for a particular project and the skill set of the end user. But overall, GIS is a solution that contains all the features that we need for data accessibility and streamlining our processes.
Hi, everybody. I'm Evan Robinson. I'm with VTrans, program manager for the Unmanned Aircraft Systems program. I just want to talk a little bit today, less on the technical stuff and a little bit more about what our program has been doing, not only at VTrans, but across agencies. So just to highlight a couple of VTrans projects, this year we've been frequenting the downtown Middlebury Amtrak tunnel. We've been able to document really good change over time imagery at that project. We worked a little bit in assessing stability of rock slide up on Route 108 in, I guess, Jeffersonville, up in Smuggler's Notch. We've also been mapping our airports. We have 7 out of our 10 airports that we maintain mapped with high resolution imagery. So that's some VTrans stuff. But we've also been working with other state agencies, in particular, Agency of Natural Resources. We've been working with the geologists from the DEC on a few projects. We've most notable, the DEC used our imagery to map groundwater distribution in and around the Rutland Airport by mapping geological formations in Clarendon Gorge. And they have also used us to fly the Cottonbrook landslide up in Waterbury, Vermont. And they've used our imagery to also monitor the developments in the past year and how that landslide has increased in size and stability and instability. A little bit more, some of you may know the Vermont State Police also have a UAS program, and we have been collaborating with them not only in training but in some procedural development. I'm actually attending a training with them next week, a search and rescue specific training for UAS. So the hope is that we're able to develop some consistent and common procedures for UAS operation within the state. And that way there's just consistency across the board and we can use this tool more effectively. And finally, I'll just mention really quickly, I think the folks from UVM will elaborate, but we do have a really amazing multi-DOT training initiative underway right now that UVM is providing us with some really amazing knowledge. So that's Mass DOT, New Hampshire DOT, Maine DOT, and the Vermont State Police. And we're all participating in some really highly valuable UAS training with some really specific and technical aspects. So that's kind of the work we've been doing across agency lines, and our goal is to provide a valuable resource to any state agency that would like to use our services. We don't have a lot of resources in Vermont, and it's highly specialized, so we would like to be able to transfer our knowledge and have other folks use us as a resource.
Is there anybody that has something that they wish they had had time to share and now they have that opportunity?
Hey, Summer, I got a question for you.
Yep.
This question is for Dan and relates to the use of the tank. How can you comment a little bit about how the tank functioned with various flows in the culvert?
Yeah, so there was testing done. It was kind of hard to see in the photos I have. Basically, the parts of the chassis are cut out to let water kind of flow through without creating a sail effect, kind of. It worked pretty well. It's fairly compact and heavy, unless you put it in a strong moving stream. It seems to move right along. I have some video I can probably upload to the page if anyone's interested. So does that kind of answer your question?
Yes, thank you.
Hey, it's me. It's me again. I almost forgot. So I'm adding to the chat right now a link to the VTrans UAS publicly available imagery. Did that come through for everybody? Oh, no, I gotta hit send. And this is where the VTrans UAS program is hosting all of our publicly available imagery. And this is a spot where you can see what we've been up to last year and this year. And for GIS professionals, this is available. They can download these data sets and pull them into their own projects for use. So everybody should check that out. Thanks, that's it.
Great, you answered my question.
Okay, good.
And I think the one thing that wasn't clear to me is, Todd, if no one else has a question. So the municipalities will own the iPads in the end and take on the stewardship of their data? Or is that where your role ends, or?
Yeah, we're
evaluate?
still working through with contracts and legal, except exactly how long the time period should be, or if we should have certain I guess thresholds that the municipalities meet before it's kind of hands off. And yes, the intention is that they would own the iPad at the end.
Got it.
Hey, Summer.
Yes.
And is there a schedule to put the HIVE 2 in service, or is that still awaiting something?
So the final reporting on that project and the deliverable device, I think, is happening in the next several weeks. I'm not sure if there's a timeline for actually rolling it out in service, but it should be pretty much ready to go in the coming weeks, is my understanding.
And is that a single thing, or is there more than one? Or and if there was interest in more than one, whose court is the ball in to make that happen?
So right now, as it stands, there's well, 1.5 devices. There's one finished inspection vehicle. One of the goals of the project was to document all the componentry and the assembly, so that VTrans personnel would have a quick and accessible way to make additional units. I think so. It's my understanding that as part of the project is providing VTrans with the capability to make additional units, if that decision is made.
Great, thanks.
Thank you.
I guess while we wait, I have a question for you, Sarah. For the GIS apps that you showed us, do you know how much it gets use or how much knowledge there is within the agency of its availability or the work that's being done? I asked just because it's the kind of the first I'm seeing of it.
Summer, can you repeat that? I didn't hear all of it.
Oh, I was just wondering, for the information you showed us of work that you've been developing, do you know how widely known, like within the agency, it gets used, or is like know that it exists? It's sort of just a general question.
Are you talking about the projects that I just went over?
Yeah.
Yeah, so depending on the project, the storm damage assessment application was used pretty heavily in the last major storm, the Halloween storm, and the northwest part of the state, the governor used that to declare an emergency, and so that application is pretty widely used, as well as the morning report is that, it's not the governor isn't using it, but that's used pretty heavily too. It just depends on the application, but as far as I know, that most people are aware of within our bureau and probably the agency aware of what we're doing.
Got it. All right, so we're ready to start breakout session B. We have all the participants on the call, and Ken, I think your hand is still raised, but you don't have a question. Okay, great.
Correct on both counts.
Okay, so automated system for classification and geolocalization of U.S. traffic signs.
Hello, can everyone hear and see my screen?
Yes.
Great. Yep, so my name is Daniel Wilson. I'm with the University of Vermont as well. And our project is called Sign Hunter, Classification and Geolocalization of U.S. Traffic Signs. And so the high level overarching goal is that we're taking raw images captured from a roadside vehicle, and then our ultimate goal is to then use that to construct a map that contains the signs that are extracted from the images using machine learning. So there are three core components to the project. First, there's our data set. So any machine learning algorithm is extremely reliant on a good data set. So we have over 80,000 images and 55,000 annotations so far, with 181 different classes of signs. Actually, I think it's a few more now. And so an annotation is just a specification of a bounding box around a sign in an image, the sign class, which specifies what type of sign it is, and then the GPS location of that sign. So then what we're actually using that data set for is that we're training an image detector, which feed it the raw pixels from the image as input. And obviously we don't have time for a lecture on deep learning, but you can essentially think of a neural network as a giant mathematical formula. So we're feeding in all of the raw pixels from the image as input, and then we train it to output the sign type, the bounding box, and the GPS location, which are the three pieces of the annotation that we just described previously. So once we've got that, we now have a tool that can find signs and images. But in order to construct our final map, when a car is driving by, for instance, you'll see that the same sign is obviously going to appear in multiple consecutive frames. So we need some sort of a tool that merges together those redundant detections where the same sign is detected multiple times, but that doesn't accidentally merge together signs that are physically different signs from different detections. So this is our tracker. So again, I don't have time to go into all the details, but the two core components are a distance metric network and the Hungarian algorithm. So basically we have another neural network that determines how similar two signs are to one another. So if they have greater similarity, then they're more likely to belong to they're more likely to be the same sign. So then the Hungarian algorithm will then merge them together according to the similarity value computed by the distance metric network. And if we stack that full system together end to end, what we're doing is we're taking the raw frames from the video, we're putting that into RetinaNet, which is our object detector, which predicts the sign class of bounding box and GPS coordinates. We then compute how similar different detections are and then merge the similar ones together using the Hungarian algorithm. And then that gives us our final predictions for the signs. I think I just perfectly used my 3 minutes. So thank you.
Thank you for that. Up next is VAMIS. I'm hesitating to introduce folks because I'm not sure who's presenting and who's not. So,
no sweat, I got it. Hi, folks. Can you see my screen?
yes.
Okay. I'm Rick Scott. I'm the manager of the data services section in the Asset Management Bureau. And I'm the product owner for the VAMIS project. I'm here with Karen Deasy, our business lead for the VAMIS project, and Chris Adams, the ADS project manager for the VAMIS project, to discuss our poster for the Vermont Asset Management Information System, known as VAMIS. One of the takeaways from our poster is the need for VTrans to take a holistic approach to managing Vermont assets. Our roads, bridges, culverts, signals, retaining walls, the list is nearly endless, all require a level of continuous maintenance throughout their lifetimes. And since nothing lasts forever, eventually each of these will need to be replaced. Add to this that each of these assets depend on one another to maintain a continuous transportation network, and you can start to see the importance of a holistic approach to transportation asset management. Over to you, Karen.
VAMIS uses the DTIMS cloud-based solution. Our field data is collected into this platform from various data sets and analyzed. Risk assessments, treatments, and life cycle costs are developed to inform capital programs and to improve budgeting for maintenance needs. This is done by leveraging our knowledge about our infrastructure, monitoring condition over time, and accounting for actual expenses used to maintain each asset. We are working with each of our assets individually to assess needs and tailor features of the program for everything from field inspection to managing task completion. With the flexibility of the VAMIS platform, it allows the assets to access additional features as their needs change. VAMIS provides effective management by assessing various budget changes to condition, tracking progress, and managing work requests, allowing us to work smarter together towards the right asset, the right treatment at the right time. Chris?
Agile. It was made popular in software development when it was determined traditional waterfall methodology was not cutting to get the work done. Simply put, Agile is the ability to create value in a fast-paced and consistently changing environment, which makes it an effective methodology for project management. The VAMIS project was an Agile tester of sorts for how to handle contract payment provisions for vendor effort and how the team and the vendor would organize their work. The VAMIS dashboard development is broken down by asset: pavements, signs, rock slopes, culverts, etc. One of the project's key driving forces was not to develop other scheduled assets until the current bundle of assets in development were fully completed. Quality over quantity. This is perfect for Agile, as it allows for change every step of the way and provides usable output at the end of every sprint, also known as customer value. That is something waterfall methodology is not really designed to do until the very end of the project, at which time the original need, the reason for the project, may have changed, making the project less successful. I hope in this short time I've been able to convey the value this tool has provided the VAMIS project. Thank you.
Great. Thank you. You guys are right on time. And there was 3 of you. Pretty good. Up next is RFID technology for transportation signage inventory management.
Okay. Yeah, this is Tian. Can you see my screen?
Yes.
Okay. Yeah, this is a project for using the radio frequency identification technology for transportation signage management. So the team, including Professor Byung from UVM Computer Science, and myself from Electrical Engineering. So there's a traffic sign along the road. There are a lot of them. So how to do the management? So this is an important part of transportation asset management. And to do the traffic sign management, it involves a number of tasks, including the locating signs and the guardrail terminals, and record the accurate data, such as like a deployment time, manufacturer, the age and material, and quality, so on and so forth, and checking the reporting the physical integrity, like quality visibility. And also, if there's some damaged one or the low quality traffic signs, they should be replaced. Okay, so to do this management, we need to give each traffic sign a unique ID. So traditional approach, like using the barcoding, stick barcoding on the traffic sign, this is not very efficient. First, it does not support remote sensing, and can cause the contamination can affect the coding the scan, and also labor intensive because you need to scan every sign. Need to very close to each sign to do this scan. So in this project, we propose to use RFID to do the remote sensing. So this allows the remote sensing at a far distance. And also we put it in the vehicle. So when the vehicle is driving on the road, so we can do the driving speed interrogation. And also there's a wireless communication established between the scanner and the remote database on the cloud or at the other control center. So here is the system diagram showing the configuration. So we have an in-vehicle RFID reader, and we also have a handheld RFID reader. So in-vehicle reader can do the remote sensing at the driving speed scanning. And handheld, if you have a special request or special need, we can approach the traffic sign and do the scan on site. The methodology, so as I said, we have an in-vehicle RFID reader and a handheld reader. We integrate them together. And also we develop a comprehensive database to support the traffic sign management. Here just shows the lab test. So this is the RFID we put on the inside the vehicle, and this is the handheld reader and the tablet to support the data management. And here we also do some of the field tests. So this is a field test on Vermont State Road 63. And here I just want to briefly show you a short video. Okay, yeah. So this we just the RFID the antenna on the vehicle and drive the vehicle and scan the traffic sign along the road. Okay, for conclusions, we developed this traffic management system, including both the hardware and the software, and the laboratory test and field test validate the system performance. And we also made the recommendations for how to really deploy the technology on the different scenarios. And the potential impact and the benefits, so this can certainly improve the traffic sign management efficiency, reducing the cost. And also if we have all the RFID tech deployed along the road, so that we can employ many other applications like a smart road traffic management and the pavement management, the construction side safety control, and many other new ideas we can explore. Okay, that's all.
Thank you. Up next, we have remote radar inspection of concrete bridges. We have, yep.
Hello, hi. My name is Tzuyang. I'm associate professor from the Civil Engineering Department at UMass. In the following 3 minutes, I'd like to share with you one of our ongoing projects at UMass on the development of a portable radar sensor for concrete crack detection and moisture determination. This research is motivated by the fact that when concrete structures crack, especially concrete bridges crack, their structural significance is usually unknown to civil engineers in order to make meaningful repair or management decisions. From the existing technologies, we know that there are many kinds of non-destructive testing and structural health monitoring techniques that can provide subsurface information, but the challenge is lane closure is usually required, and access to the surface of the cracked concrete structure surface is also necessary. However, in the meantime, there are also other type of technologies in the area of remote sensing. Synthetic aperture radar imaging is one of them. In remote sensing, surface information of structures such as terrain information or texture information can be detected by distant measurements using electromagnetic waves such as the microwaves or even thermal infrared. The focus of this research is to try to combine these two in order to bridge the gap, to use remote sensing but to get subsurface condition of concrete structures. Now, what can we learn from synthetic aperture or SAR images of structures? Well, first of all, we know that radar images contained changes of structures' internal properties, such as materials property change, and also with the change of the structural geometry, such as cracking. Now, from our previous research, we have learned that moisture content variation is the main factor affecting the radar images of concrete structures, which is also the reason why in the past, when people use other electromagnetic sensors, such as ground penetrating radars, they will not be able to pinpoint the condition of subsurface cracking or subsurface steel rebar corrosion of concrete structures because they could not remove the effect of moisture. However, in this research, there's a fundamental dilemma. The purpose for using electromagnetic sensors is to be able to detect subsurface cracks, but in reality, it is impossible to verify the inspection result without disrupting verification. So that's why we start with simplified artificial cracks. We believe that the solution can be obtained by performing extensive parametric study, understanding the background and understanding that what kind of parameters in SAR images is most important for us to perform subsurface condition assessment for crack detection. What we have learned is that moisture distribution can change the entire SAR image. And this kind of change is related to the amplitude and also its distribution. In the meantime, we also found that the coupling between the amplitude and the distribution of the amplitude shows a significant correlation to what we call crack volume. And this crack volume can be modeled by the product of crack length, crack width, and crack depth. So crack depth detection can be achieved by removing the information of crack length and crack width from the crack volume. So from this calculation, we can determine crack depths. Now, what about the practicality? At UMass, we have been developing this kind of portable radar sensor. Currently, we already have a portable radar sensor at a weight of about 2 pounds. With this kind of 2-pound sensor, we can use just one inspector and carry it to inspect bridges, or even to fly it on the drone. Now, we also have tried inspecting real concrete structures using this kind of portable radar systems. We found that the findings that we have obtained from laboratory samples can be applied to real structures, and we have published results in the past. And in the end, we'd like to thank USTOT, TIDC for the financial supporting of the system. And with that, I will conclude with my presentation. Thank you.
Thank you. We're on to the last presentation, fiber optic sensing technology for structural health monitoring of bridges.
Hi, everyone. Can you guys see my slides?
Yes.
Hi, everyone. My name is Andres Biondi. I'm a PhD student at the University of Massachusetts in the Department of Electrical and Computer and Engineering. I work on the Professor Shin Wen 1. I'm here today to present us our current research, which is titled Fiber Optic Sensing Technology for Structural Health Monitoring. Now, the main idea of this project was basically to develop a system which allows to monitor long infrastructure such as bridges, pipe, railways, and do it in such a way that we don't have the need of individual and localized measurements. So to do that, we have been using what's known as a Brilliant frequency, which is a methodology that reads backscatter light from a fiber, and this signal is directly relational to strain and temperature. Now, the way how this system works is we use what's known as a BOTDA system or controller. A light is shined into the fiber, and the fiber the controller will read the backscatter signal, and if any change has happened throughout the lifespan of the structure, we will be able to see it, because prior to the installation, we collect a base signal, and all our measurements are based and compared to that signal. Now, we have already implemented this into a field test, and this was implemented on a rail bridge located in New Hampshire. We provided different tests, and in this test we measure the status of the bridge without having any load on it, and then we also measure while any Amtrak train was passing by, and we have found that there are significant there's some increase in the Brillouin frequency, which is related to the amount of strain that is provided on top of the bridge, and that can see here on this on these pictures. So as the train passes by, the frequencies shift, and then that tells that if throughout a long time monitoring, if this frequency keeps increasing, that means that the bridge is suffering of any type of deterioration. And currently, we also implemented this textile, this sensing system into other bridges, and hopefully we'll be able to enhance the knowledge on this type of system and be implemented not only on bridges, but as well as in pipes or railways. Thank you so much.
All right, thank you. With that, we conclude session B, and I'm going to open up to questions and just have folks raise their hand, and I will call on you. Hopefully we have lots of people raising their hand this time. Dan?
Yeah, so I had a question about the radar system. You said it's a 10.5 gigahertz. Is that are you doing a frequency sweep from like 1 to 10 gigahertz, or is it a single tone? Or is it a? Are you doing a wide bandwidth sweep, or is it a single tone at 10.5 gigahertz?
It's a single tone, but the bandwidth is about 1.5 gigahertz. So I use continuous waves. It's not like impulse. So you can call it as a single frequency inspection. Okay,
so you're doing like a network analyzer kind of. You're doing okay. Neat.
But at much lower cost.
Right. That's very neat. Thank you.
Yeah, sure. Thank you.
All right, well, thank you everyone for joining us. I'm not hearing any questions. This will be recorded and available on the website, and we encourage folks, if you think of any questions, to follow up with the presenter to get your questions answered. I've enjoyed hearing everybody's work. Thank you.
Thanks, Summer.
Thank you so much.
Thank you all.
Thank you.
Thanks, folks.
Bye.
Bye.